So let's look at some statistical analysis with the data and reanalysis products. I think most of you know what reanalysis products are. They are a blend of models and data, dynamic interpolation to reconstruct past history of climate. You get nice gridded products, but they have all kinds of issues as well. Nonetheless, those tend to be the best things we can get as far as past climate are concerned, and they give you full fields at all kinds of time scales. To the extent that you can trust them, you can do lots of analysis. And what you'll see is when we look at the structure, time scales, and amplitudes, spatial scales of these interseasonal variabilities for the South Asian monsoon, these are all diagnostics. They don't necessarily mean we know the processes by which the scale selections happen, by which the amplitudes are determined, by which the time scales are determined, and so on. Nonetheless, these kind of understandings obviously help to build theories and then seek more data, our field programs, satellite data, reanalysis, modeling, etc., to look for details, predictive understanding, predictabilities, and so on and so forth, right? So let's start with this nice figure here, which is showing standard deviation of 10 to 90 day filtered GPCP precipitation anomalies. So GPCP is Global Precipitation Climatology Product. I bumbled CMAP before. That's the CPC CPC mapping project, okay, which is a Ping-Ping-Xi's precipitation product. So there are several precipitation products which combine in situ data, satellite data, and so on, but sometimes they don't combine different data, etc., etc., etc. Nonetheless, the large-scale structures tend to be pretty similar. Okay, so what do we see here? So if you look at the standard deviation of filtered, so when you take the total signal and you filter it at certain time scales, 10 to 90 days or intraseasonal oscillation, intraseasonal variability time scale, and the explained variance that remains when you do this filtering is always critical, but we don't discuss that too much. But it is important, of course. And here is the same thing for interannual variability of the June, July, August seasonal mean for the period of 1997 to 2007. And this is the amplitude of the annual cycle computed as JJAS mean minus December, January, February mean for the same time period. So what you see here is that the intraseasonal variability, standard deviation variance is similar to this annual cycle, and in fact is much larger than the interannual variability. The interannual variability here turns out to be the largest in the marine ITCZ region here, and of course you get the orographic Western Ghats where you get some high standard deviation as well. But you can see that there is a somewhat of a similarity over this domain between the annual cycle and the standard deviation of the intraseasonal time scale going from 10 to 90 days. So this is the time series of normalized monsoon ISO index between June 1 and September 30th, which is typically considered the monsoon season. That amounts to 120 days for a sample of 11 summer seasons. The ISO index is defined as 10 to 90 day filtered GPCP rainfall anomaly averaged between 70 degrees to 90 degrees east and 15 north to 25 north. So this is over the so-called core monsoon zone, where typically we define the active break periods and various indices of intraseasonal oscillations. So the time series is normalized by its own standard deviation. Open circles and squares indicate peaks of active and break conditions. So when it is positive here, the normalized index, that's the active period, and when it's negative, that's the break period. So as we said, during the active period there is rainfall over the core monsoon zone, and you can see clearly there is interannual variability, and as we saw before, there is multi-decadal variability in the monsoon, which also amounts to multi-decadal variability not only in the extremes but also in the intraseasonal oscillations. As for the scales, you can see the vertical and the horizontal scales and structures here. Sorry. So this is the horizontal and vertical structure of dominant interseasonal variability. Regressed 10 to 90 day filtered GPCP and zonal wind and meridional wind anomalies at 850 hectopascal with respect to the ISO index from here. So you regress that to extract the structures. Again, explained variance is not maybe very low, but they are still process insights. You can get this. So this is at zero lag, so that's the active condition, and you can see here the rainfall is positive with the cyclonic intraseasonal anomaly in circulation, and over the deep tropical region, especially focused on the eastern Indian Ocean and southern tropical Indian Ocean, you have the, of course you are crossing into the southern hemisphere, so you have to be careful, but you have the anticyclonic circulation. So you have this phasing of north-south structure. There is, as I mentioned before, in the extremes case, there is also this east-west structure that remains, and there is also a similar thing happening here in the Pacific, which is related to the East Asian summer monsoon, which has similar timescale intraseasonal variability as well. And C and D, the anomalous. So here are the break period, which is exactly the opposite. So you have the anticyclonic circulation, so high pressure subsidence, negative rainfall anomaly at intraseasonal time scale, whereas the convection, rainfall, and cyclonic circulation is over the deep tropical ocean. And you can see this large scale structure here as well, which we will come back to when we see that the 10 to 90 day scale is actually split into the 10 to 20 day time scale and 30 to 60 day time scale. And associated with this north-south pattern, there is the local Hadley cell. Obviously, when there is rainfall over the subcontinent, you have rising motion and then sinking motion over the tropics, and you see the baroclinic structure there, and you switch this around, and again remember these are intraseasonal anomalies, filtered anomalies. Okay, there is a scaling involved to show the vertical velocities at the same time scale. This is just showing the spectrum of rainfall anomalies for 20 summer seasons, again taking the JJAS for IMD high resolution gridded rainfall averaged over the core monsoon zone. This is the zonal wind anomalies at 850 hectopascal. That's a B here, and C is the same as B but averaged over 85 to 90 degree east and 10 degree north to 15 degree north, so that's focused on the Bay of Bengal. And D is same as B but for meridional wind anomalies. And the main point to note is that when you look at these multiple variables, you do see the clear peaks at multiple time scales. This is the 95% confidence level for the periogram method, and the dotted lines that you can barely see here represent. So the spectra are calculated using the periogram method, and the dotted lines represent 95% confidence level. So without going red noise null hypothesis, this is the standard way of doing spectra to show that the peaks you are seeing are in fact significant and they can be trusted for the time scales that are emerging out of these. So there are differences in the Arabian Sea, Bay of Bengal, the land core monsoon zone, and there is also a north-south pattern within the subcontinent in terms of the core monsoon zone versus peninsular India, core monsoon zone versus northeast India, and so on and so forth. But the main message I will take is that there is a 10 to 20 day time scale which has a smaller spatial scale, and 30 to 60 day time scale which has a much larger spatial scale, which you can see here much more clearly. So Percentage of total daily variance of 850 hectopascal zonal winds explained by 10 to 20 day mode. You can see this Rossby wave structure here. So this is explained this time scale, which is generally referred to as a quasi-bi-weekly time scale of 12 to I think 12 to 18 or 12 to 20 days or so. Here we are looking at 10 to 20 days, but the mesos, the structures associated with the propagations involve the Rossby waves. Here the Rossby waves are asymmetric, shifted to the north by the mean monsoonal winds and so on, and the 10 to 20 day band is related more to the monsoon depressions, which are many times the low pressure systems are in the synoptic time scale of 3 to 10 days, but nonetheless these are multi-scale systems. But the 30 to 60 day time scale, you can see, has a large scale structure going all the way to the western northwest Pacific in the tropics. So that is much more related to the interannual variability as well. This is here a complicated figure showing here the spatial structure and amplitude of the 10 to 20 day mode. So we are focusing on just the 10 to 20 day mode. Regressed 10 to 20 day filtered anomalies of OLR. We'll go back. 850 hectopascal winds B. And C here is the 200 hectopascal winds with respect to a reference time series of 10 to 20 day filtered zonal winds averaged over this 85 to 90 east, 5 to 10 north. So this is more in the Bay of Bengal with zero lag, where most of the meso propagation happens. Only regressed wind anomalies that are significant are shown, and D and F are so D is in the previous figure. We'll go back. F so D is the let me make sure I don't screw this up. D is OLR. E is the 850 hectopascal winds, and F is the 200 hectopascal zonal winds based on 20 years of summer data. So you can see the structure here in OLR. It's focused on the Bay of Bengal extending into the subcontinent, so that's consistent with the meso and the northwestward propagation of the 10 to 20 day time scale features. And associated with that you have, so low OLR is convection, right? Tall clouds, cold temperatures, outgoing long wave radiation is minimum here with respect to the filtered time series. 850 hectopascal winds show the cyclonic circulation and the anticyclonic circulation that goes with that. And here is the D is the D is the OLR again, E is the 850, and F is the so D is the OLR. Again you see the OLR here, the structure. E is the 850 hectopascal and F is the 200 hectopascal winds. Basically you can put them together and get the structure of the 10 to 20 day interseasonal oscillation, which has a predominantly northwestward propagation. Okay, so be careful. Here we are looking at OLR anomaly, here we are looking at total OLR, and one has to be careful. So 200 hectopascal winds show the interseasonal time scale westerly anomalies and the anticyclonic circulation. So you have cyclonic circulation at the lower level corresponding to the low OLR, and so on and so forth. To look at the coupling between convection and low level winds, here OLR and the divergence at low level 925 hectopascal averaged over 10 to 15 north are looked at. There is all this random averaging which correspond to where the maximum signals are, and these kind of strong signals at interseasonal timescales also indicate including that high standard deviation compared to the interannual anomalies means predictability is potentially high because the signal to noise ratio is high. at intraseasonal timescales. So the coupling between convection and low-level winds for the 10 to 20-day mode, lag longitude plot of regressed 10 to 20-day filtered anomalies of OLR, and divergence of 950 hectopascal wind. So if low-level divergence and OLR are in phase, strongly related to each other this way, that means there is a convection happening and the low-level divergence is related. So when you have negative, obviously it means convergence. So you have negative OLR anomalies and convergence, positive OLR anomalies and divergence. So you have a systematic propagation. Here is 0 when you have active phase averaged over this region, which is usually the Bay of Bengal, but you can see here you're going in longitude and the time is going up because this is lag and this is lead. So you're starting this way, so you have this northwestward propagation. Here we are averaging over 10 to 15 knots, so you mostly see westward propagation of the dry and wet systems. This is a similar figure for the 30 to 60 day mode, regressed 30 to 60 day filtered anomalies of OLR 850 hectopascal winds and 250 hectopascal winds, and D and E and F are showing OLR 850 and 200 hectopascal winds. Again, you will see now the large scale structure. So the 10 to 20 day is much more confined in space, whereas the 30 to 60 day is got this large scale but still has this north-south pattern, still has this anticyclone-cyclone anomalies associated with this, and here are the corresponding OLR 850 hectopascal winds, 200 hectopascal winds, and this is the C is the boom boom boom. I'm doing back and forth. This is 200 hectopascal, this is 200 hectopascal zonal wind. So this gives you a sense of the structure of the 10 to 20 day and 30 to 60 day winds, and these are the wave number spectra. So the top panel shows symmetric east-west wave number frequency spectra normalized by its right background, calculated for 11 JJS seasons for 1997 to 2007. A is the precipitation from GPCP, B is the 850 hectopascal wind anomalies, zonal wind anomalies. Bottom panel show north-south wave number frequency spectra, again for averaged over 60 east to 100 east, 12.5 south to 25 north, 12.5 south to 29.5 degree north, using precipitation and U850 anomalies. So you can see the predominant wave number is between 1 to 3, which does matter because this is what determines the propagation speeds and scale selections happening in terms of waves, driven by diabatic heating and the Doppler shifts associated with the winds and wind shears and so on, which we will get into a little bit later on. But you can go to my tropical dynamics course and see more details about how waves are affected by background winds and vertical and horizontal shears. This is just showing the evolution of convection and relative vorticity at 850 hectopascal, or a cycle of the 30 to 60 day mode, regressed 30 to 60 day filtered anomalies of OLR, and relative vorticity at 850 hectopascal with respect to the same reference time series that we saw before, from a lag of -20 here to +15. So you can see the evolution of the system here. So if you look at the vorticity and winds, you can see the correspondence with the convection, and OLR and vorticity coupling again indicates the convective processes, but basically you can see the phase that is positive here, negative here, slowly shifts, so you end up the with the northward propagation of this signal. You can see now by -10 it's here, and by -5 and at 0 active period you have the maximum action over here over the Bay of Bengal, but stretching all the way into the Pacific, and you have opposite phase here. And then as you go to +15, again the phase comes back to where we are here in the -20 phase. Okay, so you have the 30 to 60 day, which does mostly northeastward propagation, as opposed to 10 to 20 day, which does the northwestward propagation. Okay, so this gives you a sense of the structures, timescales, amplitudes associated with the ISVs. This is a bit longish as a podcast, which generally I tend to avoid, but it was good to keep these figures together and get a sense of the spatial structure, temporal structure, propagation, spectral peaks, what else? Amplitudes, right? And we will build on this as we go forward.